All right, here it comes. This is the second video for Unit 6. Really typical, classic AP free response question, but you also see bits and pieces of this showing up in the multiple choice, is when you are given a function that is defined by the integral of another function. So let's look at this one. We have a piecewise function, little f. This graph over here is the graph of little f of x. It's defined below on the interval 0 to 16, check. And we're told that big F, the antiderivative, is going to be the definite integral from 0 to x of this function. Part A, they're going to ask us to find big F of 5, big F prime of 5, big F double prime of 5. And of course, we're going to show the work that supports our answer. Part B, we're going to determine all the critical points of big F on the interval 0 to 16. And we're going to classify these critical points as relative maxima, relative minima, or neither. We're going to justify our answers. Part C, we're going to determine the absolute maximum. If Justin was in the room, I'm sure he would say absolute maximum. That means we're going to have a lot of work to do in order to prove that we truly have an absolute maximum on that interval. And we're going to show the work that supports our answer. And then finally, because life isn't complicated enough, they're going to give us a new function. Big G is going to be 5 plus the antiderivative from 3 to x squared of f of t dt. And we're going to find the equation of the tangent line to G at x equals 4. So with all of that said, let's jump into this problem. Here we go. Part A, evaluate big F of 5. Well, this starts off easy enough. Big F of 5, well, how was big F defined? Big F is the definite integral from 0 to x. Big F of 5 means I want the definite integral from 0 to 5 of f of t dt. We've known for a really long time that a definite integral represents the area bounded by a curve in the x-axis from 0 to 5. I've got a trapezoid and I have a triangle. Folks that want to see this as a rectangle, you can see a rectangle there, and then a triangle here, and another triangle. Feel free to do that. I'm going to approach this as a trapezoid. As a trapezoid, there's my first base that has a base of 1. There's the second base. The length of that base is 3. 1 plus 3 is 4. Multiply by the height, which is this piece over here. I'm still at 4. Divide that in half, I've got 2, but it's a negative 2 because I'm below the x-axis. I'm going to add on to that the area of this triangle. Base is 2, height is 1, 2 times 1 is 2, cut it in half, 1. Big F of 5 is negative 1. Okay, easy enough. There's nothing new there. Now, big F prime of 5. Let's stop and think about that. Big F prime means take the derivative of big F. Okay, this is big F. And then evaluate that answer at 5. Big F prime of 5 means take the derivative of big F the way it was given to me and then evaluate it at 5. Your notation has to be precise here. You are going to lose points if you do it in the wrong order. Derivative of the function, get an answer, then evaluate it at 5. Well, let's see. I have the derivative of an integral of a continuous function from a constant up to a variable. We all know exactly what's going to happen here. This is f of x. Why can't I write f of x? And I'm going to evaluate that at 5. F of x evaluated at 5 means f of 5. I go on over to my graph. Here's where x equals 5. What's the y value there? 1. Done. That's big F prime of 5. Big F double prime of 5. Well, let's see. We've done this before. I want two derivatives. So that is a derivative of a function which is defined by an integral of another function. And then I'm going to plug in x equals 5. We know this part here in the middle, the derivative of the integral of a function, is just f of x. That's the piece in the middle. Then I'm supposed to take a derivative. then I'm supposed to evaluate the derivative at 5. The derivative of f, another way to write that is just simply f prime. F prime of x evaluated at 5 means find f prime of 5. Now that we're finally at little f, its derivative would mean I would go over here to where x is equal to 5, and I need the slope of the tangent line. Well, here's a problem. The tangent line, if I'm coming in from the left, has positive slope. If I approach 5 from the right, my tangent line has a slope of 0. I see that the derivative from the left and the derivative from the right are not equal to each other. Our conclusion would have to be big F double prime of 5 does not exist because little f of x has a sharp turn at x equals 5. Okay. And for all my calculus students watching this, we are not using the word cusp point anymore. You could say big F double prime of 5 doesn't exist because F has a sharp point. You can say big F double prime of 5 doesn't exist because F has a corner point. You can say big F double prime of 5 doesn't exist because little f is not differentiable at x equals 5. You want to impress me with your vocabulary, but we have to stop saying cusp. I've heard from several calculus teachers that writing the word cusp most likely will not earn you the point, and good golly, who wants to lose points? Not me. All right, here we go. B, determine all critical points of big F on the interval 0 to 16. By critical points, what I mean that big F prime is equal to 0 or that it's undefined. If either of those two things happen, then we have a critical point. Now let's be careful. Let's be really careful here. We know that big F prime is the derivative of the integral from 0 to x of f of t dt. We already saw that in part A. We have shown that because of the second fundamental theorem, we just get f. So from now on, you know that if I'm asking you questions about f prime, I'm really just asking you about little f. But you have to show this. You want to make that really super abundantly clear on your paper that you know and you are using the fact that big F prime is equal to f of x. So we want critical points. If big F prime of x is equal to 0, what that really means is that little f is equal to 0. Well, where is the graph of little f equal to 0? I see it over here at x equals 3. I see it over here at x equals 11. X equals 3 and x equals 11. Those are critical points. Now, where is big F prime undefined? That would mean that little f is undefined. Where is this graph undefined? When I look at it, it's continuous, so it's defined everywhere. So this doesn't happen. We don't need to worry about that. We just have to look at it. X equals 3 and x equals 11. Now, great, we've identified the critical points. Now we need to classify the critical points. And so here's the conversation we need to have. At x equals 3, what is happening with the graph of f? I see that f is changing from being negative to positive. And I'd want to say something like, since little f changes from negative to positive at x equals 3, this implies big F of x has a relative minimum at x equals 3. I know it has a minimum because if little f is changing from negative to positive, and little f is the same as big F prime, if the derivative of big F is changing from negative to positive, then big F has a relative minimum. I'm going to try to write that a little bit better at x equals 11. So we could say, since f of x changes from negative to positive, This implies big F prime changes from negative to positive at x equals 11. But if, at x equals 11, wow, I said I was going to do a better job and I didn't. Little f changes from not negative to positive. Over here at 11, we're changing from positive to negative. My apologies, make sure you catch that. At x equals 11, little f changes from positive to negative. If little f changes from positive to negative at 11, then that means that big F prime changes from positive to negative at 11. That means that big F changes from increasing to decreasing at x equals 11. Well, if I have a function that changes from increasing to decreasing, that means that big F has a relative max at x equals 11. Done. Sorry that was not my best work yet. But let's go through that thought process again. I wanted critical points of big F. I know that a critical point means that the derivative is equal to 0 or undefined. So I take the derivative of big F, which we know is little f. I have to ask myself, where is little f equal to 0 or undefined? That happens at 3, and that happens at 11. I've identified my critical points. Now I need to classify the critical points. F of x changes from being negative, below the x-axis, to positive, above the x-axis, at 3. Since little f changed from negative to positive at 3, this means that big F has a relative minimum at x equals 3. Similarly, at x equals 11, little f changes from positive to negative. Because little f changes from positive to negative at 11, from positive to negative at 11, this means that big F prime changes from positive to negative at 11. That means that big F changes from increasing to decreasing. Therefore, big F has a relative max. Done. All right. Same graph, new question. Determine the absolute maximum of big F on the interval 0 to 16. Okay, absolute maximum. It is a 4-step process. You have to do all 4 steps. The first is you identify your candidates. Where might you have an absolute maximum? You might have an absolute maximum at any place where you have a relative maximum. As we already saw in part B, you have a relative max right over here at 11 because f changes from positive to negative. So my candidate is x equals 11. Second, you evaluate big F at 11. So to find big F of 11, that means I need to find the integral from 0 to 11, f of t dt. If I'm going to do that, I need area. I have negative area here. I have positive area here. I tried to pick a nice graph. We have a trapezoid. That length is 3. That length is 1. Add those together, that's 4. That's 1 there. Okay, we have an area of negative 2. We have another trapezoid here from 3 to 11. That base is 8. From 5 to 8, that base is 3. If that base is 8 and that base is 3, 8 plus 3 is 11, times 1 is your height, and cut that in half, I'm getting a positive 5.5. So big F of 11 is going to be negative 2 plus 5.5, which is 3.5. That's the second step. We identified our candidate. We evaluated the original function at 11. The third is you evaluate F at the endpoints. Evaluate big F at endpoints. Well, my first endpoint is 0. If I want to find big F of 0, I'm going to find the definite integral from 0 to 0 of f of t dt. How much area is there from 0 to 0? I have no area. At x equals 16, big F of 16 is your definite integral from 0 to 16, f of t dt. We've already decided that this area here is -2. This area here is positive 5.5. The only area left to find is from 11 to 16. Another trapezoid. Area here is 5. The length of that base is 5. The length of that base is 2. 5 plus 2 is 7. Times 1 is 7. Cut it in half. -3.5. -2 plus 5.5 is 3.5. Minus 3.5 is 0. Last step. We're almost there. We identified our candidate. We evaluated the function at the candidate. We evaluated the function at the endpoints. Last thing, land the plane, buddy. State your conclusion. Okay, my conclusion. Determine the absolute maximum value. They want the value. The conclusion should be the absolute maximum value of big F of x is 3.5. That's it. But this is all the work that needs to be shown in order to get that justification point. Normally, a question like this could be worth 2, 3, sometimes even 4 points out of 9 on the free response part of the exam. You want to get this process under control. I've seen great growth in my students this year. Couple of folks still not quite so sure on the flow. You have to get the flow under control. Okay, last part. Same graph, new function. We're told big G is 5 plus the definite integral from 3 to x squared f of t dt. We want to find the equation of the tangent line of x equals 4. Equation of the tangent line, that's pretty typical. That means I need a point. That means I need a slope. The point comes from finding big G of 4, big G being this new function. The slope comes from taking the derivative of G and evaluating it at 4. So here we go. Big G of 4, remember, new function. Big G is going to be 5 plus the definite integral from 3 to 4 squared, that's 16, of f of t dt. So I need to find the total area starting at 3, going all the way to 16. I'm going to save myself some work here. We already know that that's 5.5. You've written it on your paper a couple of times. I think we even determined that this area over here is -3.5. So G of 4 is going to be 5 plus 5.5 minus 3.5. That's 10.5. We get 7. If G of 4 is equal to 7, that means that I have the point 4, 7. Great. Now I need big G prime of 4 to get the slope. Take the derivative of the function, the derivative of the function 5 plus the definite integral from 3 to x squared, f of t dt, and then evaluate that at 4. Well, order is important. We take the derivative of this function in here. The derivative of 5 is 0 plus the derivative of an integral from a constant up to a function of f of t. It's going to be f of x squared times 2x. That's your extended second fundamental theorem of calculus. And then evaluate at x equals 4. So let's finish this off. We don't need the 0 anymore. F of 4 squared times 8. That's f of 16 times 8. F of 16, I'm going to get that from the graph. I go over to 16. The y value there is -1. We have -1 times 8. That's -8. That is your slope. You have a slope. You have a point. The equation of the tangent line is y equals -8x minus 4 plus 7. Done! Done, 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 done. Golly, that one went so much better than the earlier one did. That's it. That would be the kind of question I would expect most of my students to be able to at least do parts A, B, and C, and I'd give you about 15 minutes for that. You You have to be hustling to get through to Part D, but this is fair game. And if you consult your journal entries, you've got several examples, plus the last unit test where we went through questions like this, and that should really help get everybody prepared for the reassessment that's coming up. That should also help you get ready for the trimester exam. This will be great study material for the AP exam. You really couldn't ask for much more than this. Good luck.